All right. We're trying to find inverses of matrices because that's super exciting, and we're going to use what we already know, which is Gaussian elimination. In fact, gauss-jordan elimination. Super, super good. So the way this little piece is going to work, so the first thing will be just a quick general story of why this is really AX equals B. In the next piece or so, we'll have a deeper connection to elimination matrices, which we know are the same as row operations coded. That's going to be very powerful. And then a quick example of a 2 by 2. All right, or a simple example. Okay, so the plan is this. So we're trying to find, so given A, so the game. Let's make this bigger. The game is given A, someone hands you A, n by n, find a to the minus 1. And again, this means that we have a matrix which is n by n. We put on our t-shirt. I mean, it's a given. And it means that if we pre-multiply or post-multiply A by this matrix, then we get the identity. Right. So let's imagine we have this version. Let's imagine we have this part of it. This looks a little bit like AX equals B. AX equals B-ish, right? Although this of course is, in general, this is an m by n, this is an m by 1, and this is an m by 1. Here we have square matrices, and instead of vectors, instead of vectors here, we have two square matrices. All right. We're determined to make everything AX equals B, because then we don't have to think, right? Wow. The thinking comes into seeing that it's AX equals B, and then using our methods from before. So let's just sort of set up a generic 2 by 2. So imagine we have, okay, so solve this. Okay, so let's consider, because some monks told us to do it, consider A times Z equals I, this problem, right? So where we know, of course, we know the identity matrix, we know A, someone hands you A, and then we want to find Z. And again, these are all n by n, n by n, and n by n. But let's just sort of take a 2 by 2 kind of general example. And we'll write it like this. We'll say A times, this will be Z1. This is the vector it's a 2 by 1, right? So 2 by 1. The first column and the second column. We'll just make them clear, right? So this is Z. This is nice to do, isn't it? And this has to be equal to our identity. And let's write that out. So that's 1, 0, 0, 1. Now we know how we can think of matrix multiplication in sort of, or carry it out in more kind of higher level ways. And one of them is that when you multiply a matrix with another matrix, the first one, in this case A, goes in and simply multiplies the columns one at a time. So this, right, advanced wrangling, let's put wrangling, gives us A times Z1. So that's a vector, right? Because this is a 2 by 2 in this case, times a 2 by 1. And then this is an A Z2. Right, so both of these are actually 2 by 1s, 2 by 1s. And then if we sort of zoomed in, can I do that anymore? No, I'm there. This is a 2 by 2, this is a 2 by 1, 2 by 2, 2 by 1. Right, so this still equals the identity matrix here. So let's just identify, so to speak, the vectors inside of this. So, this equal sign is an important thing. We actually can see there are sort of two equations here, right? So there's this first column equals this column, and then this second column equals this second column. So, and you can see how this would generalize, whereas if this was Zn, right, Z1 through Zn, we'd have all of these columns of the identity matrix equaling A times Z1, A times Z2, A times Z3. Now, what I might want to add here is that these are the unit vectors, right? So this is I hat, J hat, right, from calculus, if you like, and that would keep going. Fine. Well, let's leave that in, I hat and J hat. Just a little side note. So we have these two problems to solve. Let's write them out separately. So now we have, so it's equivalent to solving A times Z1 equals 1, 0, and A times Z2 equals 0, 1. So these are AX equals B problems, right? These are AX, that's a sad little ampersand. These are our friends AX equals B. So we know how to do this. We do row reduction, right? Gaussian elimination, and then, yeah, so, and then back substitution would all work. Now, of course, when we do row reduction, we're working only on A, so we do exactly the same steps. So that's an important, so this is a note, we would use, you know, I'll put it up here. It's right out of space. Right, we would use same row reduction because we're just trying to make A into U. We would make A become let's get that right. Make A become U, right, with row reduction for both equations. So the light bulb, let's have a light bulb. Ooh, I can make a light bulb. Right, so we have a little light bulb situation. Boink, 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 boink. Let's make it a little bit yellow. We have a light bulb, and we say, let's just solve, let's do it all at once. Do all at once. And when we get to elimination matrices in a little bit, and with a let's do all at once. When we get to elimination matrices, we'll see this is even better. So with a super augmented matrix, I don't know if that's really the right term, but there you go, super augmented matrix. So instead of solving each one individually, with the little augmented matrix here and another one here, we'll do it like this. So you would actually do this. A bar, right, the vertical bar, identity, identity, do row reduction on this thing. This is awesome. What if hashtags will last? Octothorpes, excellent objects. So this is an n by n. This is an n by n. So this whole thing is an n by 2n, n by 2n matrix, the whole thing. And we're going to do row reduction. So what happens is we do row reduction. In fact, we'll do more than Gauss. So basically use row operations to turn the left, to turn A, let's say A into first U, right, the upper triangular matrix, then in fact I will go all the way to, we'll actually keep reducing it. And whatever, we just let the, on the right hand side, we just let I change and change and change. I will change into a to the minus 1, the inverse. We have to do a little more to show that that's more than, because in fact if you go back here, it's a right inverse. Right, I'll leave that there. So this is just a slight note. We're finding the right inverse. Right, we multiply on the right, inverse of A, and then later, or soon, we show it's, so this is actually finding this, we show it's okay. It's the true inverse. It's a true inverse if the pivots are all there, the true inverse. Okay, that's sort of enough. This is a good thing to remember, or understand. So, okay. This is true. Maybe I don't need those brackets. It's a big deal. Only works if A has n pivots, right? So none of them are missing. So we'll get to that in a little bit. Okay, that's a pretty good page. I should put more light bulbs on. I'll put more light bulbs on. Okay, so example. Yay. Example. Yes. I'll just give you a 2x2 just here. So it's the one we had in the previous piece. -2, -2, 4. So you're handed this, find the inverse. Boom, you go construct the super augmented matrix. And then we'll do row operations, and we'll do them in the right way. -2, 4, 1, 0, 0, 1. And I know I have to, I'll make another one that just has a 3x3, another piece that just has a 3x3. You should say it, right? Usually the case is if you 2x2s, you've got to do them, and then 3x3s are enough complication to see how it would work for larger and larger systems. Not always, but generally speaking. Row operations, we always do the same thing. So this is, it's not equal to, but it's same kind of system, but we're, right. Okay, so row 2 prime, we're going to get rid of this one. Row 2 prime is row 2 minus something times row 1. Let's put on, I can still put this here. Okay, so what do we have? So we're trying to get rid of the -2. So that's that. This is pivot. This is pivot 1. That goes on the bottom. So let me point to that. Pivot 1. The whole thing here is L21, the multiplier, L21. Right, and I'll write it as -2/3. Okay, so that's our row operation, which is a little nastier here than the normal. Now that's fair enough. That's exactly what happens with, usually what happens with inverses. Things get a little hairy. So I've got everything. Right, so we're adding, so it turns out if you look at this, right, this is adding 2/3 of the first row to the second row. So the first row doesn't change. There are a lot of profound things here. We'll get to them. Beautiful things. Somehow there are parallelograms here. True. So yeah, so 2/3 of the first one. So that changes our 3 into 2, and we're adding it. So that's good. So that will give us a 0 as desired. And I got carried away and wrote these things down. I should not have done that. So we're just the first row. Right, so the first row is unchanged. Let me maybe put this in blue. So a 0 here. Now we have to concentrate. We're multiplying this by 2/3. So it's 4/3. So this is really going to be 4 minus 4/3. Right? And 4 is, what is that, 12/3? So this is going to be 8/3. Yeah? Maybe? Yeah. 8/3. And then we're adding 2/3 of this character to the next one. So it's a bit easier at the start on the right. So we're adding 2/3 here, and we're adding 2/3 of 0 to 1. So that's going to be just 1. Right? That's our first step. So because this is a simple 2x2, we're already at U, right? So this is U. This is the U matrix. This is the first pivot. This is the second pivot. Already there. The next one to get the chop is here. And now we work the other way. All right, good. Good. So one more row operation. Same structure, but now it's row 1 prime is equal to row 1 minus something times row 2. We're not going to call these multipliers in the same way because the L's only belong in a lower triangular matrix, but So I won't label them in the same way, but we still have we have D2 is here on the bottom. We're going to divide this second row by, whoa, that's good. We're going to divide the second row by 8/3, which will put a 1 here, then we multiply it by -2 to get this number, and we subtract it. Right, so I guess I don't want that in, I'll put that in red, because craziness. 8/3, this is the second pivot, that's all of D2. And then on top, the thing we're trying to get rid of, which is -2. So again, we're going to end up adding something. So all of this number is 3/4, right? If we look at this thing, this whole thing here, the two minus signs, it's 6/8, so it's 3/4 plus. Let me do that. All right, so good. We're not going to change the second row. That's the plan here, 2/3, 1. And we're changing the first row, so good. All right, so blue. All right, so a simple thing happens here. We're just subtracting something from 0 from 3, so that doesn't get changed. All right, good. And then we're adding, adding 3/4 of this blob to this blob. The way we've constructed it is, of course, that will get rid of this -2. So that has to be 0. You can check that for yourself, but I mean, you should always check that. Here we can see it's working. So 3/4 times 8/3 is 2, and then we add that to the first row. Then we have 3/4 times this blob. So that's a half. So this would be 1 plus, maybe I should write it like this, 2/3 times 3/4. Right, so it's 1 plus a half, so I'll write that as 3 halves. And then we have 1, just get rid of that. And then we have 3/4 of this blob here being added here. So it's just 3/4, like that. So we're almost there. Very important things have popped out. We're almost there. We just have to make this into a 1 and this into a 1, right? We're trying to make the left-hand side into the identity. And so this is something we touched on once. So there's one more row operation. Let's call it another row operation. And it's going to be that row 1 prime is equal to 1/3 of row 1. So what are we doing? We're actually dividing it by the pivot. Yep. And then row 2 prime is 1/8/3 of row 2. So those two things happen. And again, we're dividing it by pivot. So divide by pivots. So this is where we would already have been in trouble. But this is sort of a clear case as well. If we have a missing pivot, there's a 0 instead of a non-zero number, then we can't divide through. Right. We could if we were evil, crazy people, but the universe would go pop. Okay, so we're going to divide. I'll keep this piece here. Maybe I can't do it. We're dividing through. We've still got all this stuff. So divide the top row by 3. So let's do that. So we go through. There's a 1, which was the plan. 0, also part of our plan. Dividing through, we get a half there and a quarter there. Right, the 3's disappear. Amazing. And then we're dividing through by 8/3 on the second row, and we can think of that as actually multiplying by 3/8. So 0, 1, 2/3 times 3/8 is a quarter, and then 1 times 3/8 is 3/8. So so we've done the right thing. So this is great. You should really this is a good thing to be able to do. Identity. And this we're claiming is the inverse of A. So let's bring it out, and I just want to identify something. I'm going to pull out the 8. There's a 1/8 we could pull out. right? And if we do that, we end up with a 4 here, a 2 here, a 2 here, and a 3 here. This is just tidying up. Well, the monks have told us something. So, whispered something to me. They're just sitting over there, actually. It's kind of stressful. So, this is actually a special number. I pulled out 8. I could have pulled out anything, right? But turns out this is a special number. Very special, very special, very special. Okay. A very special number for A. Yeah, it's funny. They wanted me to write in gold leaf and all those things, but come on, guys. For A. It's called the determinant. I mean, the words are just not the best, are they? I've got to resist. And we'll write determinant of A and or det of A like this, or in fact, this. A couple of lines around it. This is notation for it. Yes, that's awesome. But this is more later, all right? That's a special thing. Soon I'll show you something about it, but there's something to do with parallelograms and volumes and lots of things will be connected to that. Now let's see, we had this 1/8, 4, 2, 2, 3 right here. Let's go back. And I told you at the start that this section, that was the inverse of A. Yes. Right. So how did we know that? And this is how we knew it, right? We had done this calculation here ahead of time. So this is good. C 5A, page 1. Right, so the same thing. It will work on both sides. We'll get to that. But I think this is the plan. Now, if we have 3 by 3, it's more complicated. But we just do the row reduction in the standard way. Maybe I'll just outline quickly how that works. I won't give you an example, but 3 by 3 plan. So let's say we have, and so we'll have 1, 1. We'll set it up like this. Right, put our identity matrix here, A. Let's just say we have, I don't know, 1. Just the order of attack. Now we have to get rid of 6 numbers, right? So we have to go here, 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 and then you flip it around and do the opposite. So let me label them. So this is 1, this is 2, this is the order of elimination. Right, so some shadowy character hands you a list and says, these are the ones you're going to bump off, and then they're in this order. I know, mathematics is violent. 4, 5, and 6. Right, so maybe another way is we work down the first column, we work down the second column, third column, fourth column, fifth column. There's always a staircase kind of structure here. And that's true, we just flip it around and work back the other way. But now we work up the last column, right, and then up the second to last, and so on, so on, so on, until we've got zeros everywhere, and then all that's left is the pivot matrix, and then we divide through by the pivots. And revealed will be the inverse on the right. Row swaps are something else. We have to think about that a little bit. That's a possibility as well. So okay, so this is the plan, right? Good. So you should be able to do this. We've done Gaussian elimination, so we're just using it. We've just found out that we can deploy it for this structure here, the super augmented matrix, and we're trying to solve for a very special case where A times a matrix is equal to the identity. We still have to show you that matrix works on both sides, but we've gotten some of that. Yes. All right.